Hello, mathematicians, and welcome to At Home with APS this morning. I am Miss Obenshane, and we're going to be doing some counting practice today to get started. We're going to be doing something called choral counting, which is kind of counting together. So you're going to try to match my pen. I'm going to record our count as we go, and you're going to try to count with me and match your count to my pen so that we're all counting together. And then what we're going to be counting with this morning is we're going to be counting by 120. And then after we do that and we record some patterns, then we're going to look for patterns in the numbers that we record in and see what we can find. So our first number in our counting sequence is going to be 120. And if we're counting by 120s, you would need to think about adding another 120 to that. So take a minute here and just think about what would our next number be after 120, and then the next number after that also. So just think about that for a minute. And then I'm going to just hold on to this. We'll come right over here, and this is where I'm going to record. And so we're starting with 120. Have you thought about what the next number would be? All right. Count with me then. 120, 240, 360, 480. What will be next? 600. We're going to come up here. 720. Count with me. 840, 960. Something's going to happen on this next one. Can you think about, let's just take a minute and think about what would be next if we're counting by 120 and we're at 960. 1080. That's right. We're going over to the next into the thousands. And then 120 more would be 1200. 1320. 1440. 1560. 1680. We're going to stop right there for right now. Okay, let's think about it. I'm going to give you just a minute to look at these numbers here and see what patterns you see in these numbers. What patterns do you see? Well, one of the patterns that I see is in the tens place. 2, 4, 6, 8. And then that 0 comes at the end, right? 2, 4, 6, 8. 2, 4, 6, 8. We see that pattern repeated over and over. What other patterns do you see? I think it's kind of interesting that this part goes 1, 2, 3, 4, but then 5 doesn't come next. I wonder why. Let's see if the next row kind of follows a similar pattern. 7, 8, 9, 10. But we don't have an 11 in there. Why is that? Let's see. 13, 14, 15. I was double lining these, wasn't I? 16. And I wonder if this one will be that. It might not start with a 1 and a 7 if it follows this similar kind of pattern. Why is it that we don't have a 5 in the hundreds place here, or a 1 and a 1 there? I think it's because we get here, we get to add an extra 100, right? We get to the 600, the 1200. I wonder what this one is going to be right here. Would you be thinking about that? Let's think about how many in between our rows. We're going from 120 to 720. What's the difference? That's right, it's a 600, huh? The same thing here. Let's see if that is the same. 240 to 840. That's a difference of 600. We are adding 600. Does that happen in the difference for every one of these, right? Does it happen between this column and this column? It sure does. That's also a plus 600. Same thing here, right? So then if we know that, what is this number going to be, do you think? I think you're right. I think it's going to be 1,800, because that would be plus 600 here. It would match our pattern. We wouldn't have a 1 and a 7. We'd have a 1 and an 8 because of what happens after we have a sequence of 4 numbers there that go in order. So I think 1,800 would be our number here. What would the number up here be if we started a new column? What do you think about that one? Yep, I think you're right. It would have a 20, right? So it would be 1,920, because it would be also a plus 600. So the patterns are very interesting that happen with these numbers. We're going to talk about a few other ways that you can look for patterns in numbers with an activity called palindrome. We're going to look at palindromes, and the activity is called palindromization. Palindromization, something like that. So, palindromes. Does anybody know what a palindrome is? Palindromes are either words or numbers they work the same both ways. Let me show you what I mean. If I write the word mom, I can read that this direction, or I could actually read it the other direction, right? It would still spell mom. If I have the number 121, it can be read backwards and forwards in either direction. And so, the challenge is to see if we can figure out how we can make all numbers palindromes. So if I have the number 36, is that a palindrome? Not yet. But let me show you a technique that you can make every number into a palindrome, like this one up here. What you do is you reverse the number and then you add them back together. Let's see if we get a palindrome now. 6 plus 3 is 9. 6 plus 3 is 9. Is this a number that can be read the same forward and backward? It is. So that is called a one-step palindrome. We used palindromization. Try to say that one fast. All right, what about 37? Will it work for 37 if we're just experimenting with patterns with different numbers? I don't know, let's see. If I flip it around, so this is what you do. You write the number you want to work with, then you add the opposite to it. I have a 10 here, and then another 10, 11. Is that a palindrome? Not yet. So we're going to just flip it around then and see what happens. The same way that I flipped this one around, the answer that I get, if it's not a palindrome, I flip the next part of it around again. And now let's see what we get. We did get a palindrome. This one that I used as my example, actually, right? So this one is a two-step palindrome. Let's see, what if we try, so some numbers are one-step, some numbers are two-step, some numbers might be three-step. So if we try, let's try, how about 59? Let's see what happens with this number. So if I add my 9 and my 5, I get 14. And then that makes another 10. So 154. Is that a palindrome? Not yet. So let's try adding the opposite to it. See what we get. Is that a palindrome? Not yet. Let's see. I'm going to flip it around and add again. I'm just going to kind of move this up here so that you can see it. And I have room to do it. And that is 11. And then I have another 11. 1, 1, 1, 1. That is a palindrome, right? It would be read the same way either way. So this one took 1, 2, 3 steps to get to be a palindrome, right? 3 steps of palindromization. So the challenge for you is if we are looking at a hundreds chart, so we'll just look at the top part of this, and I put a hundreds chart on our website for you to work with. How many of these numbers are palindromes? Can you make them all into palindromes by doing this palindromization process? Some of them already are, right? 99, I can already read that back and forward. This whole pattern of these on the diagonal already meet that, right? And then what did we do? We did 36 and 37. We tried those. And this was a 1-step and this was a 2-step. We tried 59 and that was a 3-step. So it'd be interesting for you to print out one of the hundreds chart and try this process and then color code a pattern on there and see what you notice about the pattern that shows up. And if a pattern can lead you to make a guess about whether a number would be a 1-step, 2-step, or 3-step number that would get turned into a palindrome after that many steps of working this process. So that's the challenge for you to think about on your own, is how many of those numbers are able to be turned into a palindrome and how many steps does it take? Can you turn them all into a palindrome eventually? I will tell you that there are a few that it takes a lot of steps. So hopefully you'll figure out which those are. All right. Miss Gaudette is all ready to come up here. And let me get this out of her way.
Hello, everyone. So we're going to be again working on a problem, a task. But that means that I need you to go ahead and make sure you have a pencil and paper, pause me, try it out before I do it, or else make sure you've downloaded the work and have done it also. Again, I'm going to do what I call teacher talk, which means that I'm going to work it out how I would approach it. So you can try it out your own way and then come with me and see how I would approach it, and you get to see different views of how different people look at a task. So let's get started. All right, we have Cindy's cats. Cindy has 3 cats, Sammy, Tommy, and Susie. Cindy feeds them on cat crunchies. Each day, Sammy eats a half of a box, Tommy eats 1/8 of a box, and Susie eats 1/4 of a box. What fraction of a whole box does the cats eat in all each day? Show how you figured it out. All right, so let's bring out our markers and let's go ahead and mark this up so we know what we're working with. What are some quantities that we have? All right, the first thing we know is we have 3 cats. So is that going to be a number that we're going to need later? Let's see. All right, we know we have, a half. We know that one. What else do we have? Great, an 1/8 and a 1/4. Now, what is the question that we are being asked to do? Thank you. What fraction of a whole box do the cats eat? And then it says in all. And then, of course, show how you figured it out. So why do you think the words in all are important? Right? That's telling us what operation to use. And again, it's not like the game operation with the guy in there and you're going in and it goes, eat. It's not the operation where we go and a surgeon will come in and work on you if you have something wrong with you. No, it's a mathematical operation. we're working on is it add, subtract, multiply, or divide it. And do you know what in all is? Great, it's addition. So let's go ahead and let's look at that. But I did ask you one thing. We had circled 3 cats. Is that number, quantity 3, going to be something that we're going to need to solve this question? What fraction of a whole box? No. It's telling us that we have 3 cats, so we need to look for 3 other quantities. So let's go ahead and do that. We know we have a half, an eighth, and a fourth. So I know I have, and our operation is addition. All right. So when I'm looking at this, I know that I do not have a common denominator. That's the first thing I need to do. I have a 2, a 4, and an 8. Can you think of what a common denominator would be for all 3 of those numbers? 8, right? Because we know 8 is a multiple of 2, 4 is a multiple of 2, 8 is a multiple of 4. Perfect. So if I have here my 8s, now we got to figure out the hard part. How do we get from these numbers to our new denominator? So I have, again, we're looking for equivalent fractions. We had gone over that in the past, but I want to make sure that you know that this is what we've done earlier is helping us out now. So how do I get from 2 to 8? I multiply by 4. So again, whatever we do to the denominator, we have to do to the numerator. So 1 times 4 is 4. Did I have to do anything to 8 to get to 8? No. So I can just bring that on down. What do I have to do to 4 to get to 8? I have to multiply by 2. And then I do the same to the numerator. 1 times 2 is 2. So let's go ahead. 4/8 plus 1/8 plus 2/8. 4, 5, 6, 7. And we were able to add those numerators. Why? We were able to add them because that is we had common denominators. That's the only way we were able to add them. If we had a number that was not the denominator, that was like a 2, a 4, and an 8, we can never add those numerators. They have to have a common denominator to be able to add them. So my question, I got 7/8. Am I done? If you have worked with me before, you know we're not done. We have to have the unit. What are we trying to solve for? And the question said, what fraction of a whole box? So we know we have 7/8 of a box. Okay, let's go ahead and let's break apart number 2. So it says here, Tommy and Susie spend much of the day sleeping. Don't we wish we could, right? Tommy sleeps 3/5 of the day and Susie sleeps for 7/10 of the day. Which cat sleeps longer? How much longer does it sleep each day? And then show how you figured it out. So let's go ahead and let's circle our quantities. 3/5. 7/10, thank you. And of course, now we got to underline what the question is. Which cat sleeps longer? And then how much longer? Then of course, show your work. Let's go back to number 1. Did I show how I figured it out? Did I show my thinking? Yeah, I showed my math. We're okay on that. I want to make sure to go over this when it's what it means by show versus explain. So we know the difference between those two. Because I know that last time we had to explain, not just show. Okay, so let's do that. We know we have 3/5 and 7/10. And then we got to figure out which one sleeps more. Again, it's our equivalent fractions. Thank you. So I know that my denominator will be 10. And easy, this one's 10, so I know the numerator will be 7. Now I just need to know, how did I get from 5 to 10? I multiplied by 2. Thank you. And then we do the same to the numerator. 3 times 2 is 6. So we have 6/10 and 7/10. Which one's bigger? We know 7/10 is bigger. So let me go back to my thing to know who slept more. Who had the 7/10? And it was Susie. So to answer my question, Susie sleeps longer. All right. Did I answer my first question? Which cat sleeps longer? I did. My next question is, how much longer? All right. So we know we have our 6/10 and 7/10. When it says how much, what is the key words, how much, telling us to do? Subtraction. So I'm going to take my 7/10 minus my 6/10, and that will give me 1/10, because now we can subtract the numerator since we have common denominators. And then, have I answered my question? I haven't written it out, right? So Susie sleeps 1/10 of a day longer. Okay. Now it says, show how you figured it out. Did I show my math here? Have I showed my work? Yeah. All right, so we're okay on number 2. Let's bring out number 3. All right. Cindy's cats often share a carton of cat milk. Sammy always drinks 1/3 of a carton. Tommy drinks 5/12 of a carton. And Susie drinks 1/6 of a carton. What fraction of the carton of the cat milk is left over? Show your work. Have you guys ever seen cat milk? I personally haven't. I'm wondering about that, where that might be. I'd have to go to the pet store and look, right? Maybe you need to also, just to see if there's cat milk actually out there. All right, sorry, I squirreled. But let's go ahead and let's look at what is the information that we need. What's the quantities? Right? 1/3 is our first quantity. Tommy drinks 5/12. That's our next 20. Thank you. 1/6 is our last quantity. So now we need to know, what is the question? The question is, Cindy's cats often share a carton of cat milk. No, that's just extra information that we really don't need, except for their sharing. Sharing is a key word for us. So let's go ahead and underline what the question is. What fraction of a carton is left over? And then show your work. Okay. So we have here, and I had said sharing was a key word for us. What is the key idea? What operation are we going to have to do when we share? Right? It's put together. It's all together. So we're adding. So we know we had 1/3 plus 5/12 plus 1/6. All right. So our work is that we're going to have to find a common denominator again. So I have 3, I have 12, and I have 6. I always look at the largest denominator, so that will help me to see if it's a multiple of the other 2. So let's see, 12. Is 12 a multiple of 3? Right, it is. Is it a multiple of 6? Yes, it is. So 12 it is. All right, perfect. So now we need to figure out, what do we do to each of these denominators to get the common denominator? So what did I do to 3 to get to 12? multiplied by 4. Thank you. So again, on equivalent fractions, the numerator and denominator, whatever you do to one, you have to do to the other. It's almost like a balancing of an equation. If you do something to one side, you got to do it to the other side. So we have here, what is 1 times 4 is 4. Did we do anything to this 12 to get to that 12? Nope. So we don't have to do anything to our numerator. What did we have to do to our 6 to get to 12? We multiplied by 2. So do the same to the numerator. 1 times 2 is 2. Then again, since we have common denominators, we can add the numerators. 4, 5, 6, 7. So I had 7/12 of a carton of milk. Are we done? Did I add that right? No. No. 4 plus 5 is 9, 10, 11. My apologies. All right, so we have 11/12. Let's make sure if we answered the question. What fraction of the carton of cat milk is left over? Did I say how much is left over? No. I said how much was used. So how can I figure out what's left over? We subtract, right? So we have 1 whole. What is the 1 whole? 1. And you're all like, wait a minute here. We have to have it in a fraction to help us out. If we're working with a denominator of 12, what is the 1 whole in a fraction? 12/12. All right, so if we have 12/12, we're going to see how much is left over. We have to subtract our 11/12. And what do we get? 1/12. I'm done. I got it. Did you catch me on that one? I heard some of you yelling out. No, we're not done because 1/12 doesn't mean anything, does it? 1/12 what? 1/12 of a carton of milk. So I'm going to have to, of a carton of milk. All right, I'm going to circle that one because that one is really, the way I did that. All right, did I show my work? Yeah. All right, so let's look at our last question in this task. So Cindy's cats love to jump in and out of their cat door. Yesterday, the cat door was used 100 times by her cats. Sammy used it 1/4 of the time, and Tommy used it for 3/10 of the times. How many times did Susie use the cat door? And explain how you figured it out. So that will get you on until enough to think about it until Thursday. We will go ahead and solve that on Thursday. So be thinking about how you would approach that and how you would explain, not just show, but explain. So we're going to go ahead and move on to a read out loud, some math literature. Woohoo, with Miss Carnes.
Thank you, Miss Gaudette. Good day, all of our friends at home with APS. This is Miss Carnes here, back with another read aloud, a math read aloud for you. This is one that we started last time. It's called If You Made a Million. It's written by David M. Schwartz with pictures by Stephen Kellogg, such a good illustrator, and this is a Scholastic book. Last time we started the book and we read about a whole bunch of different kinds of chores and jobs that you could do to earn money. We talked about the different ways that you could receive that money and also something called interest, which is money that you can earn just by putting your own money into the bank and leaving it there for a while. So today we're going to read about some more jobs and chores, think a little more about interest, and then we're also going to look at what some people in the United States earn and compare their income to $1 million. So let's get started. Okay, so today, the first big job that we have offered to us is to mow the mare's meadow. That's a big job, right? A mare is a horse, so they want us to mow her entire meadow, and we could earn $10. And guess what? We did it! Stupendous, we've made $10. So how should we be paid? We could get paid with just one, $10 bill. We could be paid with two, $5 bills, or 10 $1 bills. Or maybe we want half and half, a $5 bill and 5 $1 bills. Doesn't matter, they all are worth $10. Now, if we'd rather coins, we could have a 5-foot stack of pennies, that's 1,000 pennies in $10, or we could have a 15-inch stack of 200 nickels. That's over a foot. You could also be paid with 100 dimes, which would stack up to just a little over 5 inches. Or we could receive our $10 as a 3 1/4 inch pile of 40 quarters. So many ways to receive $10. How about spending it? We could spend our $10 on 10 kittens or 1,000 kitty snacks. They must cost a penny each, huh? Or you could take your mom to the movies. Mother's Day is coming up, you know. But maybe you'd rather save your money, earn some interest in the bank. If you leave your $10 in the bank for 10 years, it will earn $6.40 in interest. And then you will have $16.40 just for leaving your $10 in the bank. If you leave your $10 there for 50 years, it will grow to $138.02. Simply amazing, isn't it? Okay, this is the biggest job yet. We are being asked to transplant this giant tree. Wow. And guess what? We did it. We moved the tree, cats and all. So we worked really hard to earn our $100. We could spend it on a plane ticket to the beach. Maybe not right now, but sometime in the future. We could pay with one $100 bill or two $50 bills, you got it, or 5 $20 bills, or lots of other combinations. If we want to pay with pennies, we'll need 10,000 pennies, and they would make a 50-foot stack if we stacked them up. So that'd be tough to stack that many pennies. Okay, but we are still working, and guess what? We've worked long and hard, and now we've earned $1,000. So the thing we want to buy is a pet. What kind of pet could we buy for $1,000? A hippopotamus, of course. Who doesn't want a hippopotamus? We could pay with coins, or we could pay with bills. That would be a lot. They're bringing the coins in a giant wheelbarrow, and the bills are coming in a huge bucket. That's a tough way to carry money around. If you don't like the idea of carrying $1,000 around with you, you could put it in the bank and pay for the hippo with a check. A check is a document that tells your bank to give $1,000 to the person who sold you the hippo. Here's how it works. You give the check to the person who sold you the hippo. He gives it to his bank, and his bank sends it to a very busy clearinghouse in the city. And the clearinghouse tells your bank to take $1,000 out of your money. After your bank does that, the clearinghouse tells the hippo salesman's bank to add $1,000 to his money so he can take it and use it whenever and however he likes. Maybe he'll use it to buy and raise more hippos. I hope so, because baby hippos are the cutest. What if we wanted to buy a Ferris wheel for $10,000? If we use pennies to pay for it, someone might not be too happy about that. Even if we used 10,000 $1 bills, it would still be pretty tough to handle. Probably a check would be best. And we're still working away. Woohoo! Now we've earned $50,000 by building a bridge. And we've just read about a well-worn, unloved, but perfectly fixable castle for sale. And it costs $100,000. So the castle costs $100,000, but we only have $50,000. So we're short. We don't have enough. How much more do we need? Another $50,000, right? But guess what? We could still buy the castle if we go to the bank. So we could use our $50,000 we earned as a down payment and then ask the bank to loan us the rest or let us borrow it. That's pretty amazing too. Then we have to pay the bank back a little at a time, month after month, for a long, long time. But the amount we have to pay the bank back is actually more than what we borrowed. What? That's because the bank charges for lending money. The extra money is called interest, just like the interest the bank paid to you when it used your money that you invested and left in the bank. Now you are using the bank's money, so you have to pay interest to the bank. If you have some very expensive plans, you may have to take on a really tough job that pays well, so you can pay back that loan. Here's a tough one. A babysitter is desperately needed for a very badly behaved ogre, and anyone who can do it will earn $1 million. It's pretty hard to pass up. If you think ogre taming would be an exciting challenge, you can have fun and make a great deal of money too. Of course, you may not enjoy taming badly behaved ogres, or building bulky bridges, or painting purple pots. Those are some of the chores we did earlier, right? Enjoying your work is more important than money, so you should look for a job that you like or make less expensive plans. But guess what? The team was successful at taming the ogre, and so we've made $1 million. $1 million! That's a stack of pennies 95 miles high, or enough nickels to fill a school bus, or a whale's weight in quarters. Would you prefer your million in paper money? Even a paper million is a heavy, heavy load. $1 million $1 bills would weigh 2,500 pounds and stack up to 360 feet. What's the smallest your million could be? $100 bills are the largest that are made, and it would take 10,000 of them to pay for your job of ogre taming. But a check for $1 million would easily fit into your pocket or purse. And it's worth just the same as those towering stacks of pennies or bills. So now maybe we could afford to buy tickets to the moon. Or we could buy some real estate, some land for the endangered rhinoceros. But if you'd rather save your million than spend it, you could put it in the bank where it would earn interest. The interest on $1 million is about $1,000 every week, or $143 a day, or $6 an hour, or 10 cents a minute, just from sitting in the bank. If you keep your million, you might be able to live on the interest without doing any more work for the rest of your life. You might like that. Or you might think it's kind of boring. Making money means making choices. So what would you do if you made $1 million? Thank you for listening to this story with me, guys. So now we're going to think about some folks that maybe make $1 million or almost $1 million. And we're going to use a tool called place value houses. And I have them here behind me. Place value houses is an organizer that can make it really easy to read very large numbers. So here's how our place value houses are set up. They're set up each period of a number. A period is a part of a number that's separated by a comma. So each period lives in its own house. Today we're going to go up to the millions house. So we have our ones house, our thousands house, and our millions house. And in between each of these houses or periods, we are separating with a comma. So let's go ahead and look at what 1 million looks like on our place value houses. So 1 million. How many from the thousands house? None. So we don't say anything. And how many in our ones house? None. So we don't say anything. Let's practice reading our number again. 1 million. And there's what a million looks like on our place value houses chart. Now, let's think about some people that we may know of and compare their income or what they earn to a million. How many of you know who Patrick Mahomes is? You want to know how much he earns every year? He makes 1 million. Let's put this in. Practice reading. Here's how much Patrick Mahomes makes. Let's read it. 1,900,000. So he makes how much more than a million? 900,000 more than 1 million. What about Ariana Grande? How much do you suppose she makes? Ariana Grande makes, oh goodness, Miss Carnes is missing a 0. You better fix that. Let's practice reading how much she makes. She makes $48 million. 48 times 1 million. Oh my goodness gracious. What about J.K. Rowling? She wrote all the Harry Potter books. Do you know how much money she makes each year? This much. How would we read this number? $92 million. Wow. 92 times 1 million, right? $91 million more than 1 million. And almost twice as much as what Ariana Grande makes. Okay. Let's take a look at, it's a lot of cards. Let's see if I can keep this one straight. How about our Vice President of our United States, Mike Pence? He makes this much. How would we read this number? This is quite a bit less than a million, isn't it? Mr. Pence Vice President Pence makes $235,083 per year. Let's go ahead and just do the math for Mr. Pence as we wrap up. How much more would he need to make to earn $1 million? We'll work this with subtraction. So right away, we're trying to take away 3 from a 0 above digits. So we need to think about moving our tens around and trying to rearrange our number, right? So we're going to have to do some borrowing right off. We're going to have to go all the way to our millions period and borrow. Change it to 0. Make this 10 a 9. Make this a 10 and a 9. Make this a 10, now a 9. Make this a 10, now a 9. Make this a 10, now a 9, and a 10. Now we're ready to subtract using the standard algorithm. So, first digits we're working with, we have 10 take away 3. That's going to give us 7, right? 9 take away 8 leaves us with 1. 9 take away 0 leaves us with 9. 9 take away 5 leaves us with 4. 9 take away 3 leaves us with 6. And 9 take away 2 leaves us with 7. And there's nothing to subtract here. So let's see, can you see the periods or the families in this number? Here's our ones period or family. Here's our thousands. We're going to separate with a comma. So if Vice President Pence wanted to make $1 million, he would need to earn, let's read it, $764,917 more dollars. Thank you all for talking with me about money and income and reading books and reading numbers. We're going to welcome Mrs. Sears on to play some games.
All right. I'd like to make that kind of money. I'm going to move the game board over just so we can have kind of some separation there in between us. All right. Can you hear me now? Hopefully. So that was interesting. I wish I could make that kind of money. Obviously, as a teacher, don't necessarily come even close to that figure. We're going to play a game. It's called the spiral game. And how you play this game is you're going to actually need a deck of cards. You're going to need a die. And you're going to need some kind of a marker or a placeholder. So in this case, you know, if we would have put a placeholder on here with this sitting here vertically, it probably would have fallen off. We're going to be using our placeholders are going to be our sticky notes. So let me explain how this card game is going to work. I'm going to put these directions up here, at least just as a reminder of what we're going to be using. So with the deck of cards, your face cards are going to be worth some different values. All right, your ace is going to be worth a 1, your jack is going to be worth 11, queen 12, and a king is going to be worth 13, correct? Yes. Now how this works, because we're going to be using all 4 of the operations that we know, addition, subtraction, multiplication, and division, when we're going around this spiral of our cards. That's the first thing you got to do with your cards, is you actually have to make it into a spiral. So if you kind of look, I know our name, our little placeholders are here, but if you kind of look around, the spiral follows around in this pattern, and we have to go all the way from the start down to the end to finish the game, okay? Let me explain a couple of things that might happen. So the first thing I'm going to do is I'm going to roll a dice. So when I roll that dice, let's say I rolled a 4, I would move myself 4 spaces, 1, 2, 3, 4. Now with that 4, I need to decide, am I going to add that 4 to this 10? Am I going to subtract the 4 from the 10? Am I going to multiply the 4 by the 10, or am I going to divide that 10 by that 4? Well, more than likely, if I did roll a 4, I probably wouldn't choose to divide it by a 4 because I couldn't divide it evenly. I would be in those fractional pieces. So I think if I was going to do anything, I'm either going to add, subtract, or multiply. So let's say Miss Carnes rolls a 4. If Miss Carnes rolled that 4 and she lands on top of me, guess what? She bumps me back all the way to the start. Another way that I would also lose my place is if, let's say, I didn't know how to add the 4 or multiply the 4 or subtract the 4. Miss Carnes could say, you got the wrong answer. You need to go back to the space you were at. Okay, so that's another way. If for any reason I had rolled a double number, and it's going to be kind of hard because you only have a 6-sided dice, so it's got to be something under a 6. So let's say if I rolled a 4, okay, and I was on the 4, then I actually get an extra turn. I get to roll again. How cool would that be? Again, the object of the game is to get around this spiral and get to the end, okay? But whatever you roll, when you roll that dice and whatever you land on, you've got to decide which operation you're going to use on that specific card, okay? So roll the dice, move the spaces, figure out your operation, and then we're going to start to play. You got the rules down?
I think I've got them.
Okay, and remember, these rules will also be available to you on the online resources, so if you want to be able to do this at home. All right, I've got my die. You've got your die.
I've got my die.
We're going to kind of stay around. I'm going to roll my first one. I got a 1. Okay, so I'm going to go over here to this 5. So I'm going to say, I'm going to do a multiplication problem. Well, actually, I could do a division problem.
You could do any of them you want, I think.
So I guess 5 divided by 1, any number divided by itself is going to be that same number. That's how many times can 1 go into that 5? It's going to be a 5.
That's a special rule.
I'm going to take it.
Okay. Let's see how I do. You have got to be kidding me. So
She got a 1.
Miss Carnes got a 1. So do you remember, we get to practice the rule then. That means I go to this card, but Miss Sears is already here, so guess what? She's just got to start over.
I got to start all over again. Maybe this time I'll be able to run. But you got to do your operation or else I can get you.
I forgot about the math. Is this a math lesson? Oh my gosh. Okay, so I rolled a 1 and I have a 5, and I think I will do addition for this. So 5 and 1 more is going to give me 6.
Okay, I'll let you stay there.
Oh,
but
you.
I had to remind you.
She did have to remind me.
Next time I won't get to remind you. Let's see how many more turns we can get. This time I got a 5. So let's see. So 1, 2, 3, 4, 5. I landed on a 7 of hearts. So I'm going to do multiplication 1. I'm going to do 7 times 5. So I'm going to count that skip count by 5. So let's do that 7 times. So let's see. So 5, 10, 15, 20, 25, 30, 35. Am I good?
I agree. Okay, my turn. Let's see. I got a 1 again.
She's not getting very far.
Not getting very
around
far.
this.
Oh, but we get to practice another rule because I land on a jack, and jack is worth 11. So because it's one of my favorite numbers, the answer I'm going to subtract. So I'm going to do 11 minus 1, and that gets me 10. 10's a great number.
And that's actually, normally if we play, we usually make our face cards at 10. So it's probably easy to remember. All right, so you did your subtraction. All right, let me do one more here really quick. I can go 2 more. So I'm going to move 2 spaces. Remember, 1, 2. I landed on a queen. Ooh, a queen is worth 12. And I have a 2. I'm going to do a division 1 again. Or maybe I could do, there's so much fun different ones I could use.
So many choices.
I think I'm gonna do a division 1. Because remember we were talking about division earlier, and I remember they were saying about equal sharing. So if I had 2 people and I had 12 cookies, how many cookies each would we get? We'd get 6 cookies each. So 12 divided by 2 is gonna be 6.
Nice job.
All right, let's go one more time and then we'll wrap this up.
I like the way you put that in a story because sometimes that helps me to think about
Her getting a 1.
the answer. And I rolled a 1 again, so I got a little distracted there. Okay, so I make it to the 8. So 8 times 1 by the identity rule equals 8.
All right. Looking at where we are right now, I'm obviously ahead. I'd like to continue more with this game, but this is a great game that you guys can play at home. As I said, it just needs a deck of cards and a little dice, and you need something to mark your spot. But we've had a really great day doing lots of fun with lots of different math concepts today, and we really want to thank you for joining us here at Home with APS. I hope you have a great day, mathematicians.
Bye, guys.